Just a relaxing Tuesday. Nothing out of the ordinary. Wait, what's this? JWST spots giant black holes all over the early universe? Oh, that throws a little thing in the sprocket chain now, don't it? Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. Yes, we're jumping all over the place this time, especially in space. And this is something I noticed on the Twitters the other day. I believe it was probably Maya Benowitz again, Cosmic Vibration. Shout out to Maya. But basically, some of the commentary you see here, I'm like, this is brought to us by our friends at Quantum Magazine. JWST spots giant black holes all over the early universe. A little sub-headline. Giant black holes were supposed to be bit players in the early cosmic story, but recent James Webb Space Telescope observations are finding an unexpected abundance of the beasts, more than we had initially expected. That's very interesting. But hey, a fractal, hey, a dungeon master. Good to see you, my friends. Good to see you, my friend. The JWST, and again, hey, the Lambda CDM cold dark matter model, the current paradigm of our cosmological understanding, it's still got a lot of explanatory power. To overthrow that paradigm, you're going to need a lot of evidence. It seems like we're getting evidence that seems to be surprising some people. And again, you can still, because that's the thing. Lambda CDM, it's not just one thing. It's like saying, oh, the string theory. Yes, the string theory. There's like 5 different types of string theory. There's like M theory and everything. It's like very often we should be specific with our language. That's something I learned from Professor Peterson. Nobody would ever abuse that. But I digress. So what's going on here? Because before we'd seen a couple of the times like there are 6 galaxies. Oh well, one of them's at like redshift 13 or it's something crazy. It's like, oh my god, and then it gets revised on like 7. It again, still looking far away, but I believe what we had put forward before is now you start to see some, and again that's going to fall within. But if we keep on looking back and back, and we notice more and more. And this seems to be essentially a common thing. And our model says things should be a bit sparser once we get around, I don't know, like 13.5 billion years ago. What evidence would we need to change the cosmological paradigm? If we keep on seeing more and more things like this, it's like, oh, the further we go back, and this is rampant conjecture on my part, rampant conjecture. I'm not saying that this is what it is. But if we keep on going back and the universe as we know it, so to speak, is homogeneous and isotropic, and the further we keep on looking back, at least for so far, if it keeps on looking homogeneous and isotropic, might that mean that our realm of persistence as we know it might be a little bit older than 14 billion years? There was that paper from Professor Gupta. I still should spend the $30 or something to review the article from like the Royal Astronomical Letters Society or whatever it is. It's monthly publications. To rent it for 24 hours is $24. The full year subscription was like 13 grand. I feel like I highlighted that. And I'm not saying it was me. I'm going to assume the good folks at the Royal Astronomical Letters realize that most knowledge should probably be free. They're switching to open source next year, so good for them. But essentially in that paper, he had conjectured that the universe as we know is about twice as old, around 27 billion years, as opposed to the 13.8 yada yada paradigm. I mean, that's cool. I mean, that would explain a lot of this. It's like, all right, we had more time for these things to develop and everything. He also engaged I believe it was Fritz Zwicky's fired light theory, which basically as light's going, if anything happens to be in Alaska or anything, it's like, might see some redshift there. Now, that might be a possibility. I believe that even about a decade or so ago in his 11-dimensional, quantum space-time or quantum space theory, he was kind of conjecturing that too. Now, again, do we necessarily agree wholeheartedly on everything? Not necessarily. It's okay to disagree, but you look for evidence. If there are things we don't know, it's okay to not know them. But hey, Mr. Quinn, thank you for joining. We're just talking about a long time ago in some galaxies far, far, far away. Literally. But so we got all these pictures. Apparently, we're seeing a lot more. All right. Groovy. Years before she was even sure that JWST would successfully launch, Christina Ehlers started planning a conference for astronomers specializing in the early universe. She knew that if, preferably when, JWST started making observations, she and her colleagues would have a lot to talk about. Like a time machine, the telescope could see farther away and farther into the past than any previous instrument. Fortunately for Ehlers, the rest of the astronomical community, her planning was... Oh, let me embiggen this so y'all can follow along. I apologize. It's fully embiggen. There we go. Where? We'll do the other one. Doesn't really seem to embiggen that much more. JWST launched its deployed without a hitch and started to scrutinize the early universe in earnest from its perch in space a million miles away. Yeah, it's like a Lagrange point 4. Basically, that little dip there, for some reason, we get like 5 of them, apparently, for some reason, around the Earth and its orbit around the sun and stuff like that. I don't know. I was going to say words. I don't even know the right words. I'm not a gravitational scientist. We'll say that. Even if we hypothetically could, like, calculate, I don't know, big G or the Einsteinian, that doesn't mean that I know what I'm talking about. I mean, heck, people for years were like, it's like, oh, quantum mechanics. It's like, you can use quantum mechanics, but if you start to say what it is, it's like, do you really know quantum mechanics? Now, Professor Wolfram on something the other day, I believe he said he's starting to understand it, but then again, he's literally building up from the hypergraph, utilizing the ether. That's, again, bloviation. I apologize. That ADD. In mid-June, about 150 astronomers gathered at the Massachusetts Institute of Technology for I could have actually probably gone to that first slice conference. Well, I don't think I was invited. Not quite a year's past this, JWST started sending images back to Earth, just as Ehlers had anticipated. The telescope was already reshaping astronomy's understanding of the cosmos' first billion years. Groovy. So, okay, we're jumping into it right here. We'll finish the next paragraph or so. One set of enigmatic objects stood out in a myriad of presentations. Some astronomers called them hidden little monsters. To others, they were little red dots. But whatever the name, the data was clear. When JWST stares at young galaxies, which appear as mere red specks in the darkness, it sees a surprising number, with cyclones churning at their centers. I may say that cyclone might be a form of a vortex. Oh, very interesting. I'd say it's a great time to be a nerd, I claim. There seems to be an abundant population of sources we didn't know about, said Ehlers, an astronomer at MIT, which we didn't anticipate finding at all. Surprising stuff is very interesting. In recent months, authoritative observations of the cosmic smudges have delighted and confounded astronomers. Everyone is talking about these little red dots, said Xiao Hu Fan, a researcher at the University of Arizona who spent his career searching for distant objects in the early universe. The most straightforward explanation for the tornado-hard galaxies is that large black holes weighing millions of suns are whipping the gas clouds into a frenzy. That finding is both expected and perplexing. It is expected because JWST was built in part to find the ancient objects. They are the ancestors of billion-sun behemoth black holes that seem to appear in the cosmic record inexplicably early. By studying these precursor black holes, such as 3 record-setting youngsters discovered this year, scientists hope to learn where the first humongous black holes came from and perhaps identify which of 2 competing theories better describes their formation. And They just grow extremely rapidly. Or were they simply born big? Well, big black holes. That happens. Now, the observations are also perplexing because few astronomers expected JWST to find so many young, hungry black holes, and surveys are turning them up by the dozen. In the process of attempting to solve the former mystery, astronomers have uncovered a throng of bulky black holes that may rewrite established theories of stars, galaxies, and more. Huh. Now, fractal. Okay. So that's the main paper there. That's from Quanta. I tend to have some faith in Quanta and everything. It's like yeah. We got some other things. Here, space.com. This is Paul Sutter's website. Here, an article. Basically, I literally just typed in black hole and news, and we kind of go through this. Now they're asking, what is at the edge of our universe? But when you talk to an astronomer, apparently they're talking about what we can see. Because I don't know. Anything beyond that, that's a cosmologist's job. Part of me is like, I didn't even necessarily know there was a difference. Where does the astronomer start and the astronomer end and the cosmologist begin? I think I just tried to define that. I'm not saying I'm right, but basically, yeah, you delve into that stuff and then starts with a bang podcast. The cosmic gravitational wave background. It's from the Big Think. Again, take the links for what you will. They're in the doobly-doo. Again, this is from Ethan Siegel. Some folks agree with him, some folks disagree with him. But it's interesting. He talks about the cosmic gravitational background, as opposed to the cosmic microwave background. That's something that Professor Keating in the Simons Observatory are looking to figure out. They should have first light, I believe, by the end of this year or the beginning of next year, and actually start to have some data. So it's pretty exciting. But yeah, it's like, all right. So if there are a lot more black holes, which I believe we've also conjectured before, because if we're going to start to claim that the universe as we know it, our realm of persistence, if you would, is a heck of a lot larger than current observable. It's about 10 to the 26 meters. Pretty freaking huge. It's like, what, 93 billion light years. The conjecture is we're more likely, the claim is on the order of 10 to the 32 meters. Now, that might not sound like much. That's over 6 orders of magnitude larger. Roughly about 168 to, depending on if it's the radius or the diameter, several 100,000 times greater in magnitude. Maybe there'd be more supermassive black holes creating that buzz. Perhaps if we were in a hypersphere of, let's say, maximal volume, within our space-time, you're going to have positive curvature, but as you're going, it's kind of like the game of asteroids. You go, and even if you're going in a direction, there's going to be curvature at some point. It's going to look flat, but there's going to be curvature at some of the grandest scales to the point where you might actually come around again. Is that necessarily true? I don't know. Hey, Jonathan. Hey, and Benny, how did you know that I was playing the Benny Hill theme song in the background? Because I feel like I should do a video to this with like some of that music where it's like I forget that song's name. But the Benny Hill song also works pretty good too. It's like people are like, no, it's not this, and then you go over time because like I didn't really pay as much attention back then, but I'm hearing a lot of folks that have been up on the greater cosmological and sciencey stuff in space. And a lot of, apparently, folks are saying when Hubble launched, it's like, oh my God, it started to rewrite our view of the universe and cosmology. Well, duh, we're getting better data. If you get better data and you didn't have the data before, it's okay. It's okay. It's okay to be wrong. I'm wrong all the time. The amount of things that I'm wrong about in this live stream right now are staggering. But basically, yeah, they go through this. There are also other things that may or may not contribute to a potential cosmic gravitational background as well. And we'll get into that in just a bit. I haven't even looked through this yet. Constraining dark energy from the local group. This is apparently some things going on because I'm interested in this. So I think I bookmarked that for later. But where are we? Hold on. All right. So let's get into the rampant conjecture here. Yakety sax, yes. That is yes, no, that is the Benny Hill one. I'm thinking like an older, more classic one where it was. Oh, was it from Mickey? Was it from Fantasia? I don't remember. All right. So what are we going to conjecture rampantly on here? Okay, I'm going to do a series of 3 things that are from my channel for just compiling things and using them again and again. I think these might be relatable or set up a picture, at least in my head. Maybe someone smarter than me can help decipher. Let's see.
I'm going to assert this, that in between these boundaries we have a lemniscate maintained, the inversion curve, and we have 2 of these cardioids. Why? Well, we put one cardioid in here.
Right.
And we put in a second cardioid there.
Yeah. Oh. This is the big reveal of the video.
And then we say, wait a second, my favorite cardioid is
The Mandelbrot.
the Mandelbrot set. Let's scale it to match perfectly right there now.
Okay.
To fit inside of our hyperbolic construction.
Yeah.
What does it look like?
Oh.
That vertex becomes the focus of this side.
One.
So you fill in this one, and both of those focuses now have internal constructive balance. You see what I mean? Symmetry happening here.
I mean, that's neat. I mean, the reason it's neat, not just because it's a pretty picture, is just, at least with the model, that's conjecturing. We're conjecturing here. The minimal boundary of our realm of persistence is essentially the Planck time boundary. That's the constant of nature that we know is of the magnitude 10 to the negative 44. We're essentially kind of claiming that's like the base turtle of our existence, so to speak. And if it happens to have the Mandelbrot set as something that's very beautiful that people are just drawn to naturally in there, that would be a fantastic thing. Oh, we're also doing a model that's basically a double cover of the simplest non-orientable bounce 3 manifold, the Giesecke constant. And if something at the base of reality could have something like this, what might that lead to? I don't know, maybe waves pouring out or something? Oh. That's pretty
This
nifty.
is leading in just a start of the conversation.
All right, but that's the link to the doobly-doo if you want to watch more of that guy. Okay, so what does this lead to? What is the point I'm trying to get at for my random kitchen? Hey, thank you for joining, Sheepherder. Good to see you, my friend. A black hole. Oh, survive it. I think I have some very unpopular opinions about black hole. I want it to lead to like a new realm. I want to lead to new. It might. There's also a very simple explanation that might probably one of the most boring explanations. I'll do that at some point. Oh, I don't want to dash people's hopes, but it makes so much sense, and I think it explains a lot. Okay, we won't belate the point. Let's finish off. What the heck am I trying to communicate here? All right, we go back to my other video, and I was saying Einstein was right. Yes, a stunning and brave statement. All right, dreams of the past. What do we got going on?
So what I'm going to claim is you have a whole bunch of matter. If you have some type of vortex articulation where it's sucking things in and spewing them out, what happens if we were to get a whole bunch of matter going in through an incredibly small yet finite volume? If at that point it's being compressed and going under some very complex articulation at the center of our realm of persistence itself, I mean, wouldn't that be the equivalent of just compressing some?
Okay, all right. So as we're lagging out here, and I got a funny look on my face, the whole claim is, all right, the whole pitch of eternal cyclic cosmology in about 20 seconds. All right. So our observable universe, about 10 to the 26 meters. We're claiming we have a n hypersphere of maximum volume of 10 to the 32 meters. Basically, that sphere out there, everything's not driven to scale. You have something down here at a point. It's about 10 to the negative 8 meters, but it is finite. At some point, you're going to have something excreting from it, It's not a quark gluon plasma. It's a whole bunch of neutrons. It's space-time literally unfolding from like super or hypermassive black holes just emanating out. Whatever's happening over there is spewed there. You're going to have the formation of different stars, different galaxies and everything. You're going to have your clusters and everything. And then you're going to end up having supermassive. And at some point, I would probably say hypermassive black holes take over. And yeah, the cycle continues. And if we apply the whole like thermodynamics and entropy and things are supposed to kind of get like disordered, but in some orderly way or something like that, things are going to kind of spread out, right? That's the claim from that. Okay. So is there anything else that might help us out here? Now, again, it's like I see a day. Oh, I'm sorry. Fractal, you're talking about the math and everything. And yes, math would be very important here. Now, well, essentially the claim is, I actually kind of got the idea from like Professor Penrose. It's like, he's talking about conformal cyclic cosmology. Now, I'm not necessarily sure I agree with every single point that everything's just going to get cold and it's going to be time, and then the universe will kind of just do its thing. And he kind of already says, like, well, you're going to have a whole bunch of like supermassive black holes coming together, and then there'll be gravitational imprints and stuff. I'm like, okay. But at one point, I think it was in Closer to Truth channel, he had an interview. At one point, he mentioned there may exist a geometric object that might fulfill that function, something like that. I'm probably messing that up, making it up perhaps, but I remember he was stressing the geometry makes a difference. Now, if you happen to have, let's say, a double cover of something like, let's go to, let's do this. Eight, not, and 3 Sigerman. There we go. All right. So I'll go bring this up real quick. All right. So this is Professor Henry Sigerman. The whole claim is the center of the cosmos as we know it is basically cinched with a knot. This is essentially the knot right here, the figure 8 knot, the hyperbolic figure 8 knot. That's just being projected in like our 3-dimensional space, so for us to understand. And then that gives rise to a complement. So if you're looking at it from the outside, you would essentially probably not be able to see unless you had a microscope or something, but a tiny little point-like sphere. It has mass, it has radius to it, but essentially you got space-time itself, supermassive, whatever, being sucked in one side and excreted from the other in whatever process it is. I mean, I've rampantly conjectured it's going to be like a quark gluon plasma. Do I know that? No, I do not know that. But that's our claim. So, but basically it's a double cover here. So if you're going to be expecting to see double covers of things, if at the minimal boundary you literally had like, I don't know, the Mandelbrot set, it's double covering. You have all the prime numbers there. If you have all the prime numbers, you can construct all the numbers, right? And if you can construct all the integers, then you should have the ability to construct pretty much everything. I don't know. But, the last point, you were talking about math there. So, long story short, I have no idea if you can survive a black hole. I mean, I haven't tried. I don't know. But, where are we going? Yes. Now, the thing is, that was an idea I had in my model, and then I got a little adventurous. I started looking at some different things. I'm like, well, what if we looked at general relativity again? And this is something that was done on the channel a while ago. So the claim is here, this is a geometric derivation of the Einstein constant kappa. So I'll make it a little better. Hold on. I'll turn off my Benny Hill in the background to save a little download memory. So, all right, here we go. So basically the whole claim is, hold on, I'll go over here. Geometric derivation of the Einstein constant kappa. All right. So let's just go here for just a second. Okay. So the whole thing is you usually have that 8 pi, and then what do we have here? All right, that's the Planck time squared over the Planck length times the Planck mass. All right, so that's essentially, I believe, a geometric version of gravity, because they have length, they have mass, they have time. Okay, and then we need the terminal action. Terminal action is actually, I believe, it's J2, the second answer to the hyperbolic vortex equation, to the 5th power. I interpret that as red n because we have 5 dimensions: time, space, mass, charge, and temperature. All right. And that's multiplied by a terminal action there. And then we have that inversion boundary, or the point of magnetic permeability, that Planck mass times the Planck length divided by the Planck charge, which comes out to be 10 to the negative 7. So we can just divide all that terminal action there. And this gives us the Einstein constant kappa out to, I think, 11 or 12 significant digits. I think it misses the last one by like 1 or 2, something like that. But it's also based upon current form of gravity, which once you get past 5 or so significant digits, yeah, there's some error bars there, and that makes a difference here. But oh, what's the terminal action? That 0, 7, 9, yada yada. Oh, that's the fantastic point. All right, so now we actually need to go back. Oh my God, I wasn't even showing that. I apologize. I was just showing you my blank screen. Hold on, let me. Wow, worst host ever. All right, I'll go to that tab. But okay, here's the whole claim. It's in a video link doobly doo below. So the whole Einstein general relativity, basically we just set it equal to 1, or at least this part of it. So, hey, what's going on, Jen? I haven't seen you for a while. I miss you. But I want to talk to you. But there's a lot of things going on, and a lot of things you've said seem to be true, as well as Kali there. Thank you for joining. I feel like we need to set up like a cosmic council or something like that. That seems to be like the thing that different folks in different communities do. And we can share ideas. We can go back and forth. We can have ourselves a good old time. But okay, the whole claim is here. I'll just reiterate real quick again. All right, we got our 8 pi. That, I don't know, 2 spheres, 4 circles, however you want to interpret it. Then basically we kind of got gravity here. So it's Planck time squared over Planck length times the Planck mass. Okay, that's cool. And we have our terminal action, the correction point, because right around 10 to the negative 7, things start to kind of get a wee bit wonky for a number of different reasons. And we're trying to figure out that wonkiness. So we got 1 plus, it's J2. I'm starting to think that might have something to do with the bulk there, because it's the larger fine structure constant, the claim is, raised to the 5th power, or the number of dimensions we have. And then we have times this number. What the heck is that number? All right, well, we'll go back to our other thing. So our friend memes of the past. Oh God, I feel like I'm in, where am I? I don't know. It's oh God, I feel like I'm in a Muppet movie. Yes, my mind is not up to snuff. We continue. You literally just search Wolfram Alpha for this number, and you're looking for a potential closed form of this, something that makes sense. Like if you see like 2 pi, I don't know, lemniscate constant, the thing that makes the infinity sign or the figure 8. Basically, you're looking for a geometric action that might help us to interpret what's going on. So when we go through and we look for possible closed forms, okay, kind of interesting here. Oh, what's this? This one nails it head on. Negative 5 CET. What the heck is that thing? That's divided by 44. That's the name of Thad's book, 44. 44 derangements in the shape of persistence. Oh, very interesting. That basically comes from when you take so it's not within arm's reach. Basically the derangements of 5, which happens to be the number of dimensional flavors. We don't need a blah, blah, blah. All right, so the crazy claim is, where are we? All right, the terminal action and why this might, just because 1, it also hits the digits there really well, It's also used in other points in the model. You could write that in minimal notation wise if you wanted as the red n, the 5-dimensional ingredients of reality, times that, I believe that's the Embry-Trefallen constant or something. It's a very interesting thing because coincidentally, we have the ability to compute it to as many digits as we want. It's very hard to compute. It takes a lot of resources. We only know what the 5 significant digits right now, which is also interesting. And then that's just 44 is just exclamation point n, the number of derangements or permutations you can do with 5 things. And what the heck is that Embry-Trefallen constant? Oh, we get even nerdier here. Where are we? We need to go to... Oh, we don't have it on... Where's Math World? Oh my god, I didn't even put... Hold on. Let's go to the close firm terminal action. We get that. Should just bring it up. This way we have the links. It's the Embry-Trefallen constant definition. Go to our friend Math World right here. Oh my god. Oh, hold on. Still showing the same thing. I apologize. Here we go. Window. Boom. The Embry-Trefallen constant on Wolfram Alpha brings us to Math World. Is this the random Fibonacci sequence? What type of magic is this? Consider the Fibonacci-like recurrence. There you have A sub n equals plus or minus. Oh, so we have options. A sub n minus 1 plus or minus A sub n minus 2. And you basically just keep on going on. I'm like, what a second. It's literally chosen independently and randomly with probability 1/2. Well, that derives the Vizrath constant and everything. And then you can go through the more general recurrences and everything. It shows these critical values. So considering the more general reoccurrence, x sub n plus 1 equals x sub n plus or minus bx, yada yada. The limit exists for most values of b. The critical value, such that b is equal to 1, is given by that b star 0.70258. Yes, we only know what the 5 significant digits for some reason, sometimes known as the Embry-Trefallen constant. So again, I'm not a professionally trained physicist. I am not a mathematician. I'm a dude on the internet, but I'm seeing this. I'm like, all right, Fibonacci is cool. Seems to draw our attention anyway. And then it's like, wait, we're saying that something is random, or as random as we know it, at least if it's probability of 1/2, it's like plus or minus something. Well, all I know is just as a crazy person on the internet, if I'm going to claim that at some point in the center of our cosmos themselves, there exists a... Oh, God, thank you. There exists a point where there literally might be something going in, something coming out, something going in, something going out. I don't know. Is that neutron decay cosmology? I don't know. It kind of sounds like a similar point. I think we got a lot of really good ideas here, and I think we're really starting to figure this out. That's my claim. And again, we went through the Quanta article and stuff earlier. Links in the doobly-doo here, but these are questions that I have. And I do think it's absolutely fascinating about what might be going on in what we colloquially call the universe. So, yeah, that's all we really got for right now. Benny, hey, Dan, what's going on, brother? But you could say that the center, it's even Thad was used very kind of obtuse language as I'm going back and listening. Whatever's happening, like in my mind, I'm almost imagining like those moon cookies, like the half chocolate of like 2 different types. Like you got like the dark, you got like the black chocolate, you got like the white chocolate, and it's just like one side is doing this, one side. Maybe it's just unfurling space-time itself. Maybe it's just constantly looking like a Big Bang. It's a lot of fascinating things going on right now, and it's a great time to be a nerd, I claim. So that's all we got for right now. Peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, and rumor has it, 2023